Good morning, everybody. Which 8 a.m. or 11 a.m.? 11. To you. And we'll put this one over here. Send it that way. All right. So labs are going back. Make sure those go up and down the rows. We need to finish Gauss's law today, and hopefully figure out where this is all going. Okay. We left off here. Oh, darn! I've got to write stuff down. On the list of topics for the exam, one of them says, does it say integral setup only or something like that? That's my way. That's one of the tricks that I've pulled to save time on the exam. So the problem involves you needing to set up an integral. And normally you would have to set it up and do the integral. And the and do the integral part could take an additional 5 to 10 minutes, depending on your integration skills. For that particular problem, I want you to stop at the setup. Don't do the integral, just tell me how you would set up the problem, and then that way you can do the problem in 10 minutes. If that makes does that make sense? So I'll be asking you on one of the problems to just set up the integral and not have to carry it out. I do have the integral table on the exam in case you do need to do an integral. But for that particular one where I said integral setup only or whatever it was I said, I was trying to indicate that, yeah, this is like a time-saving measure. I'm less interested in your ability to do math, and I'm more interested in your ability to do physics. So we'll focus on the physics part. All right, there was that. Somebody else asked me a question about, or it said I had to remind everybody of something. I think it was that, because I got that question in both labs yesterday. It'll come to me. All right. Gauss's law. Gauss's law is the art of not doing the integral you do see and doing the integral you don't see. What the heck does that mean? Gauss's law says we take the flux of the electric field through some surface, and that is going to be equal to the amount of charge enclosed by that surface divided by a constant. So we can do integrals if we can find the charge enclosed. And by doing integrals, I mean not actually doing integrals. So let's do a plane of charge. So I'm going to draw this like edge on. Okay, but like think of a sheet, like an infinite sheet of charge. Okay, going everywhere. So just a plane. It'll be a thin plane, meaning that it's got two sides, and we're gonna throw some, I don't know, positive charge. We always just seem to dump positive charge on there, right? Okay. So when we approach anything with Gauss's law, and how do you know when to use Gauss's law? Well, the answer to that is you do it first. Gauss's law, if you can do Gauss's law, do it. If Gauss's law ends up being too hard, then fall back on like integrations of electric field, that sort of stuff. Generally, like for the exam, for your homework, you know when it's Gauss's law because it comes from the section. On the exam, we'll be talking about flux usually, right? Or something. But if you got another problem and it can be done quicker, safer, faster with Gauss's law, do it the quicker, safer, faster way, right? Whatever that means to you. But when we apply Gauss's law, we are trying to take advantage of symmetries. We're trying to make the integral on the left-hand side easier. And by easier, we mean not having to do it. So this is a flat plane of charge. This isn't, I know I drew it, kind of looks the same, right? This is not a wire. This is a flat plane of charge, right? Kind of going out in all directions everywhere. And I've just drawn it from the side. So think of common shapes that we could exploit the symmetry of for this flat plane. are there shapes of Gaussian surfaces that look like a flat plane? It needs to be a volume, so it's not quite a square. It's going to be a cube, right? So we can use a cubical. Remember, the Gaussian surface could be whatever shape we want. So let's make it easy shapes. Cubes, spheres, cylinders. Right? Don't do anything. Triangles, no good. Okay? Right? So we are going to take advantage of the cubical shape. Let's take a stab as to what the electric field kind of looks like for this sheet of charge, right? Like big tabletop of charge, right? What direction, if it's all positive charge, what direction is the electric field pointing? Away, right? Okay? So, and since the charges are equally distributed everywhere, is that away like kind of up at an angle? Well, it can't be because there'll be charge over here trying to go up, right? So what are all those electric fields going to do? They're just going to be pointing straight up, right? So we've got electric field that points straight up, top and bottom. Something like that, right? Okay, so we come in here and we draw a Gaussian surface, and it's going to be a cube. Now, again, I'm drawing it from sort of edge on, right? But like my Gaussian surface, this is going to be terrible. I'm not even sure why I'm doing that. I don't know what happened up there. But I'm trying to show some. It didn't work. You know what? There are,
draw a little line and label it cube.
there's a tool for that. It's called the eraser. All right. So there's my Gaussian surface. It looks like a square, but in fact it's a cube. We do this quite a bit in the first unit here, where everything's happening in 3 dimensions, but we only draw the 2-dimensional picture. Because if we do it any other way, it's going to be messy. So we just got to remember that this is like a cubish shape, kind of around. Okay. Anyway, now I've mixed 3D and 2D, and oh my gosh. Okay. So what does this flux integral side look like? Let's talk about directions of area. What direction does the area point for the sides of this cube? There's 6 sides, isn't there? So there's a top and bottom flux. So there's an area vector that points like that. There is an area vector that points like that, isn't there? There's one down here. There's one on this side. There's one sort of this direction, and then there's one in the back direction, right? 6 directions, 6 faces of this cube, right? Are any of those fluxes 0? Which ones?
All the sides.
Every side. Everything that's not the top and bottom face. Why are those all 0?
No charge.
Ooh, well, we haven't done charge and closed yet. What direction are the area vectors compared to the electric field vectors? They're all perpendicular on all 4 of those faces. And the dot product between any 2 vectors that are perpendicular to each other is 0. So this integral here, okay, the only area we need to worry about is the area that's up here, okay, and then the area that's on the bottom, right? That's what we're after. So I come over here, I realize this integral, I'm not going to do the integral because my dot product is going to turn out to be really simple, and then I just have to add up the area. So my flux becomes E times A for the top plus E times A for the bottom. Now, are those both positive fluxes? Yes. Why are they both positive? They're both going away. They're all in the same directions, right? A dot product is positive when the 2 vectors are parallel to each other. A dot product is negative when they are anti-parallel to each other, right? So because the angle on the top, area vector points up, electric field points up, same direction, positive. Because area vector points down on the bottom and the electric field points down on the bottom, 0 degrees between those vectors, and so both of those fluxes will be positive. Okay? I should probably indicate that the red ones are my electric field. Okay, so on this left-hand side, I just get 2EA, don't I? Where E is the electric field and A is the area of the top of my Gaussian surface and bottom of my Gaussian cube. Okay, so now I need to know Q enclosed. This is the charge that's enclosed by my Gaussian surface. Now, if we went and just dumped plus Q on there, that's the total amount that's spread all over the plane. So how do I find the amount of charge that's only contained inside my imaginary Gaussian cube? Ooh, we have an area, don't we? Right? Can we leverage something that we've used before that gives us an idea of the amount of charge per area? Oh, sigma. Remember sigma? Sigma was the total charge divided by the total area, right? This is a uniform charge density, meaning the charges aren't like all piled up somewhere and spread out. They spread out evenly. And so if I take my charge on the surface, it'll be sigma times an area. So now my charge enclosed, right, is equivalent to the area that I'm using to enclose it. If I make that area the area of my Gaussian cube area, I should be good to go here, right? So this is going to be equal to sigma times A all over epsilon naught. And now I solve for the electric field. What cancels? Yes! Why am I so excited that that area cancels? We don't want it to really be dependent on the Gaussian surface, right? Now, in the other examples, like in this one right here, it was the distance away from the wire. We did want it to depend on the distance away from the wire, right? Here in the point charge, yeah, it depends on how far away you are from the point charge. So there's elements of my Gaussian surface that survive, which are okay. But in this case, I really don't want it to depend on how big the imaginary cube is that I make. So that's kind of handy. And then, wow, sigma over 2 epsilon naught? That's it? Well, the answer is yes. We actually did this one before in chapter 22 also. This is the result for a thin, infinite plane of charge. Notice that that magnitude, it's a magnitude only, it's not a vector, but what would the direction be for this?
Away.
If it's positive charge, it would be away, right? If it was negative charge, it would be towards the plane, okay? Notice that that is the strength of the electric field both above and below the plane. It's identical. What's something else that jumps out at you that is strange, amazing, or miraculous about this answer? Sigma, constant or variable? It's constant for the given situation, right? Like we can change it, but that doesn't, like it's not, sigma doesn't change depending on how far away we are from the plane, right? 2, constant or variable? Constant. Epsilon naught? Constant. Where's the distance in this? Shouldn't the electric field get weaker the further away we go from a charge? For a plane, it's completely symmetrical. Those electric field lines are going to keep going. Are they ever going to tangle and cross? Are they ever going to be able to spread out and not run into the neighbor that's right next to them? No. The electric field here will be constant, far away, close to. This is, I mean, the engineers do this all the time. They'll have a curved surface of something like an antenna or things, and they know the electric field is spreading out in all directions, but if you get close enough to the surface of the antenna, what does it look like? a plane. And so you go, okay, well, the electric field strength at the surface of the antenna will be sigma over 2 epsilon naught. You know what it is, right, at the surface of the antenna, right? And then you can make educated guesses, like it falls off as 1 over r squared, maybe if it's spherical. Like, it's a really handy result that sort of like, can that really happen? The answer is yeah. It's exactly what happens. There's a feature called a ground plane antenna that takes advantage of this. So that's not just a mathematical oddity. It's an actual, you can apply this one to different situations. Okay, let's do a little slight difference here. Okay, in that I want to do like a plane of charge, but now it's thick. So like it's infinitely thick. We don't know where the bottom is. Okay? And we just have the top surface that we deposit the charge on, right? Okay? So this is kind of our setup here. Okay? We recycle almost exactly what we did up above. We use a cubical Gaussian surface. We apply everything. But how does the flux side of my integral change? There's still no flux coming off the sides. There's no bottom. So what does that make the left-hand side? Yeah, it's not 2EA, it's just EA. Okay? Because there's an area right here, there's an electric field vector right here, and there's nothing down here. Right? There's no electric field down in that material. The electric field's only existing above it. Okay? So that's EA. Q enclosed still is sigma times A over epsilon naught. And so the electric field of a thick plane, so I better be careful here. Electric field, this is a thin plane. And the electric field over here for a thick plane, okay, is going to be sigma over epsilon naught, or half the value that it would be if we had 2 sides to work with. So that right there is an example of how we don't reinvent the wheel. We have a different situation. It's still like this cubic Gaussian surface, and we are just making sure we're clever about figuring out what the flux is through that cube, which in this case is just E times A on the top surface. We don't have a bottom. Sides still don't matter. And we can kind of quickly get the result. All right. Let's do quiz. We are, okay. Gauss's law for a sphere, non-uniform charge density. We're really kind of going to go wild now, okay? So we are going to do a case where we have a sphere of charge, and its charge density goes as a constant times its radius squared, which means there's no charge density at the middle. At the very center of this sphere, there's nothing. And as we go out, we get more and more charge density. We are going to find the electric field of this sphere. And we're going to find it both outside and inside this charged object. Okay. So let's see here. Let's see. I'm going to draw this like this. Is it going to? I love cheating. Like this. I like cheating when I draw, not other ways. So this is my actual physical sphere. We all clear on that? The black line, this is the actual sphere, and it's got, it's full of, that was wrong. Change tools, right? This is my solid actual sphere. Okay. We are going to find the electric, let's go outside first, okay? So we know that this sphere has the charge density I'm showing on the screen. And so now I've got to go and figure out a Gaussian surface and how I'm going to do all this. So is there a symmetry in this problem that is impressing itself upon your mind? Your choices are cubes, cylinders, or spheres. Spheres. Why does sphere? Because it's a sphere. That's the line of thinking you need to have, right? Okay. Oh, spherical chart. Okay, sphere, right? Cylindrical thing, cylinder. Flat thing, cube. So I'm going to draw a Gaussian surface. Now, of course, this should be all in 3D. I'm just drawing it in 2D because that's my ability. But I just have to remember that this is not a circle. This is an actual three-dimensional spherical imaginary balloon that I am drawing around my real physical charged sphere. And I'm going to set up and I'm going to use Gauss's law to find this thing out, right? So I've got flux on one side and I've got my in charge close on the other. Okay, I don't do the integral, I do C, meaning that I write down E and then A because I want to, everything we're doing in this class allows us to collapse that integral. The dot product works out. The area is just the, what is this the area of? Surface area of the, which one? The Gaussian surface, my imaginary balloon, right? So my imaginary balloon has a, I'll call it R outside. It has a radius I will call capital R. That's the physical thing. All right. And so let's see. So that it's going to be E times the surface area of a sphere, which have we remembered what that is? We memorized what that is yet? 4 pi R squared. How many of you are going to make the mistake of writing down 4/3 pi r cubed? Well, now I am, Mr. Balogh. Thank you. 4/3 pi r cubed is what? It's the volume, right? 4 pi r squared is the surface area. It's a mean trick that the universe managed to put together there. Okay. So now, what do I write down for charge enclosed? We have a charge density here, right? We need to find the total amount of charge on this sphere. So how do we do it? Can we just throw big R into this equation for rho and say we're done? No, that would be the charge density at big R. But what about the charge density halfway through? What about the charge density of the middle? What about the charge density 3/4 of the way? What about the charge density at an infinite number of points along the radius moving from the center to the outside of that sphere? What are we going to do? We have to integrate to find the charge. Gauss's law is all about not doing the integral you do see and doing the integral that you don't see. And where is the integral that you usually have to do that you don't see hiding? It's in the Q enclosed. So to find our Q enclosed, we are going to integrate all the little contributions of charge on that sphere. We have done this before. We did this in chapter 21. It's the extra stuff I threw at you, so at this point it wouldn't be so bad. So that's going to be lambda rho dv over the volume for all the same reasons that we've had before. I'm kind of going a little bit fast here. How are we going to cut this sphere up? Tiny onion layers. Okay, we're going to do onion layers going out. We're going to take advantage of that radial dependence, right? It's going to be the same all the way around. We'll take a surface area and then we'll bump it out. So this is going to be the integral of rho times 4 pi r squared dr. And we're going to go from 0 to r on that thing, we have to plug in what our actual rho is. It's ar squared, 4 pi r squared dr from 0 to big R. The law of constants in here, there's an a and a 4 pi, and then the integral of r to the 4th dr from 0 to r. What's the integral of r to the 4th? Too easy. R to the 5th over 5. Evaluated from 0 to big R, which means that the Q enclosed is going to be 4 pi a big R to the 5th over 5. So there's my charge enclosed. That is a lousy, oh my gosh, that was a fail 5 is what that was. Okay, that one wasn't much better. Here's my charge enclosed. So now I know what my charge enclosed is. It's 4 pi a r to the 5th over 5. And I got to remember I also have a epsilon naught along for the ride. And so I can go ahead and solve this for the electric field. What cancels on both sides? What's the same on both sides? The 4 pi. Can't do anything with my big R's and my little r's because those are different. This little r is r out. It's the radius of my Gaussian surface. And the big R is the radius of my actual physical sphere. So that leaves me with the electric field outside being equal to a times r to the 5th all over 5 epsilon naught r squared outside. Now, the thing in the box is not a general solution. It's the solution for this particular sphere everywhere outside of it. If I take a look at it, I can see that it does go as 1 over r squared, doesn't it? And would I expect a spherical distribution of charge to have like a point chargey type shape outside of it? Yeah, that seems reasonable, right? I mean, we've seen how spheres mimic point charges and stuff. All the other stuff, the AR to the 5th, and that's basically kind of like KQ. It's constants that are specifically applied to this situation. So I like the 1 over r squared thing there. That seems pretty reasonable. And wherever I go outside, as long as I'm outside, not inside, as long as I'm outside, that should give me the electric field at any point around this sphere, which is pretty handy. All right, but what about inside? Can there be electric field inside of this thing? Is there charge inside of this thing? Yeah, right? There's charge throughout it. The only place where there isn't charge is at the center, right? But everywhere else there's a different amount of charge. And if there's different amounts of charge, there can be electric field all over the place inside this thing. So if I'm going to find the electric field everywhere inside the sphere, that suggests that I need to draw a Gaussian surface where? Inside the sphere somewhere. So that's what I'm going to do. I'm going to draw a spherical, and it's going to be spherical again because the charge goes as r squared. I'm going to take advantage of that symmetry. And I'm going to have a radius r inside. And I'm going to set up Gauss's law, E dot dA equals charge enclosed all over epsilon naught. All right? We don't do the integral, we do C. This is going to be E inside 4 pi r inside squared. Same exact reason that it was that for the red stuff up above. Okay? But now, what is the charge enclosed? We've kind of done this, right? We've done this already. The integral is already sort of set up. Is it still charge enclosed and adding up all the charges? Is it still the charge density in the volume? Are we still going to do onion layers? Yeah, all of that stays the same. What's the only difference? Our bounds. Are we going to go all the way out to the edge of the sphere, the physical sphere? No, okay? We're just going to go out to the inside. So my charge enclosed is going to be 4 pi a from 0 to r inside of r to the 4th dr. Which means that my charge enclosed, right, is going to be, what is that, 4 pi a r to the 5th, and then we put in r in, over 5, all over 5. I think I got that right. Yep. Okay. So there's my charge enclosed, 4 pi a r inside to the 5th, all over 5. Now, okay, so what's on the same on both sides of my statement here for Gauss's law? The 4's are the same, the pi's are the same, and the r insides are the same? I got an r, I got 2 of them on this side, and I've got, so 5 minus 3. So what am I left? I'm left with E inside is equal to A times r inside cubed, this is weird, all over 5 times, oh, I forgot my epsilon naught. I usually forget epsilon naught. It's always along for the ride. All right, this doesn't feel good, right? What is this trying to tell me? What are some extremes we could put this through? What's a number we could put in for r inside that would be easy? 0. Okay, what happens if we stick 0 in there? That would be 0, 0 cubed. Oh. So at the center, the electric field is 0? Why would the electric field be 0 at the center? We know there's no charge there, but so what? In every direction you look, from the center of that sphere, you've got charge all around you, right? Positive charge. And all those field lines would have to leave those positive charges, and then when they get to you, they'd have to what? Tangle, intersect, or terminate on a negative charge. Well, there's no negative charge at the center, and they can't tangle or intersect. So what must the electric field be at the center? Has to be 0, and that says it's 0 at the center. Ooh, okay, so we're looking up. If I had ended up with an E inside where the R was on the bottom and I had to put 0 in there, I would have gotten a divide by 0 error and I would have had infinite field and I would have had to go back and check my math. But that seems to be okay. What's another place we could check? Big R. Okay, so great. I throw big R in there and it says AR, big R cubed over 5 epsilon naught. So what? That doesn't mean anything. What's another place we could put big R? What should or must be true at the surface of the sphere? The electric field should be what? The same. Right? The equation for inside, the equation for outside at the place where they meet should be equal. Otherwise, there's some weird charge thing going on. Something's inconsistent. So if we put in, if we use E outside and we put in big R, well, that's A big R to the 5th over 5 epsilon naught. And then the R outside becomes R squared, big R squared. Down here, if we put in big R, my inside is A R, big R cubed over 5. Is that the same? Oh. This is A R cubed over, those are the same thing, aren't they? So my equation for inside and my equation for outside end up with the same value at the place where they meet. That's a good sign. I'm fairly confident that the two things in the box are true for this particular situation. So what would you do if you were presented with a situation where the surface or the volume charge density was different? How does the problem change if I change rho? What changes? The charge integral, right? You got to redo the charge integral. But does the flux side change? No, same thing, okay? If it were a surface charge density instead of a volume charge density, you still go back to chapter 21 where we did all of those, right? We calculated surface charge. We found the total charge on something, whether or not it had surface charge density. If you end up with cylinders, okay, then you use cylindrical symmetry, but it's still based on R. You just got to remember it's either the surface area or volume of a cylinder. So I basically covered all of the geometries that you're going to be up against. Now, of course, Gauss's law is both useful and more difficult when you have non-symmetrical situations. But we don't throw any of those at you because you need like Taylor series expansions and Green's theorems and other things that I've forgotten how to do. And you don't have time to worry about. All right, what happened? My lecture went away. I hit a wrong button. Here we go. Let's push this, okay, and see what we can't use Gauss's law for in describing some pretty interesting situations. So let's here's a conducting shell. It doesn't matter that I drew this thing correctly or anything. What I'm trying to say here is that everywhere sort of inside here is solid conducting metal, okay? But there's a big cavity on the inside of this thing, okay? And we're going to drop some positive charge onto this conductor. What is the electric field inside of that conductor? 0? Why 0? Well, where does the charge go? So we put positive charge on there, right? Say we put, 5 positive charges on there. Where do they go? So it's a conductor, that's a clue. Conductors allow what? For charge to move through it, right? So that total amount of charge will spread out, okay, and try to get as far away from each other as possible. Okay? So the outer edge of this conductor will be charged positively. Okay, and so I'm asking, well, what did I ask? Did I ask for the electric field in this area? Or did I ask for the electric field inside here? Let's tackle not in the material first. Let's tackle the electric field inside the cavity. Okay? How much charge is enclosed inside that cavity? 0. What's the electric field in the cavity? 0. From chapter 22 arguments, we would say kind of what you guys were saying. The electric field lines, you can't have positive charges on the inside because if you did, there'd be electric field lines on the inside. And all those electric field lines, right? Like if I had positive, 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 then this one and this one and this one, right? They'd all have electric field lines heading towards the center. And they can't cross or tangle or anything. So in essence, they can't exist. So that's how we know the charge goes to the outside surface of a conductor. It's because it can't go anywhere else and maintain an equilibrium, a static situation where those charges aren't moving. So that means that any metallic thing that you sit inside of will have an electric field of what? What metallic boxes do you sit inside of on a regular day? Your car? But Mr. Balogh, my car has windows. Turns out it doesn't matter that much. The cellular signal in your car is less than it is outside of your car. Why? This is called a Faraday cage, okay? After Michael Faraday. And you saw one in a video a little bit where they put over a radio. But the same thing happens to your cell phone, okay? You may have noticed that your cell phone signals attenuate when you're like inside of a house or a building that doesn't have, like if it's, your home probably doesn't have a AT&T or Verizon or T-Mobile, thing in it, right? Some buildings, right, the cellular providers install interior antennas, right, so people can maintain strong cell phone signals inside the building. But if you're in a building, I mean, the walls aren't made of metal, but there are metallic things in them. A lot of the structural components of buildings are metal, be it rebar or metal 2x4s that are used to frame walls or something like that. And those can interfere with wireless signals, things like that, because the electric fields inside of conductors in static equilibrium are zero. So why does this make your car a safe place in a lightning storm? Acts as a Faraday cage, meaning that even if your car is struck by lightning, what will the electric field inside the car be? Close to zero, really close to zero. Okay? All right, so let's extend this a little bit further. And let's do a solid conductor. So this thing is solid, although that didn't work. Where'd my circle go? I think it interpreted my squiggles as erase this. That was funny. All right, so I've got this conductor. It's full of stuff, okay? And I want to find the electric field inside this conductor. We drop some charge on it, plus Q. We now know where the charge is going to go. Where's it going to go? It's as far outside as it possibly can, right? And so I realize I made a mistake. Not here. I made a mistake in a demonstration. I didn't grab something. I don't have time to go grab it. Oh well. I will show you. Maybe I'll show you Monday. I know we're doing exam prep, but I'll bring it. Okay. I'm going to show you that you shouldn't put metal in a microwave. I'm going to show you why. All right. But we know the charge is going to go to the outside. We want to find the electric field inside here. Can you draw any Gaussian surface that stays on the inside of that conductor and be able to get some charge inside of it? I mean, like on the surface, but that wouldn't be inside, right? That would be on the surface. Like the closest we can get is right up next to the surface, right? We could do little ones over here and crazy shaped ones over here, and it doesn't matter. All of those surfaces that I've drawn have exactly how much charge inside of them? Zero. So what's the electric field inside of a solid conductor in electrostatic equilibrium? It's also zero. So until next Wednesday, the electric field inside of any conductor is zero. On Wednesday, we're going to start electrodynamics. We've been doing electrostatics the whole time, where the charges don't move. But for now, right, we know the electric field inside of any conductor in electrostatic equilibrium is going to be zero. So we can get all kinds of crazy shapes with our conductors, right? What if we had a conductor that looked wow. I don't know what that is. Maybe that's a plant seed of some kind, a metallic plant seed on an alien. I don't know what this is. Where would the charges go? If this were the conductor, where would the charges go? As far away from each other as possible. Where is that? The outside. Only now the outside of this thing has pokies and it has innies. So where does the most charge go? Wait a second, Mr. B. It's supposed to like evenly spread itself out, right? Yes, it wants to get as far away. It wants to get into a position that is electrically minimum amount of electric potential energy. And I know we haven't talked about energy yet, but what can you tell me about charges piling up down here in this cavity? That would be closer to each other than if they pile up around this pokey part, right? Why? The electric fields of the charges around the pokey, which way can they go? Everywhere, outwards and away, right? And they're not going to run into each other, are they? So it's like we have plenty of room for charges on the pokey part. But down here in the cavity, these charges, what do all the electric field lines have to do? They have to leave and they all have to kind of squinch up through this opening right here. And so there's really only a few lines that I could draw so they don't cross and tangle. And so that means that the amount of charge in here is going to be way lower than the amount of charge I'd have where there's plenty of real estate around that pokey to pile up charge and have electric fields spread out. Why should you not be a pokey in a lightning storm? What is lightning? It's a breakdown. It's a breakdown in the insulating properties of the air. Cloud, ground. A separation of charge has taken place. Usually because rain is falling. Okay? And there's a bunch of molecules rubbing into each other. Somewhat similar to the way a Van de Graaff generator rubs felt and rubber and causes charge to build up. Or you rubbing your feet on the ground on a carpet, a wool carpet, right, between the rubber of your shoes, and you get that separation of charge. Friction, falling airdrops, moving air molecules rubbing up against each other, dust in the air. These are all causing a separation of charge. Cloud becomes positive or negative. Ground becomes opposite of whatever the cloud is. Okay? And you have this sort of buildup of charges. Now, is there going to be an electric field there? If I've got positive charge in the cloud and negative charge on the ground, is there going to be an electric field between the cloud and the ground? Yeah, you betcha, right? And now you come along with an umbrella or a golf club, or you in a flat field, right? And what are all the charges going to do that are building up in the air and around you and all that kind of stuff? They're going to go to where the pokies are. There's videos of people on YouTube that are on the tops of mountains and their hair is standing up. What's about to happen? It's about to be a lightning bolt. Okay, why is the hair standing up? It's following the electric field lines. Charge is gathering. Why don't you want to be a pokey in a lightning storm? Because that's where the electric field can be the strongest. So what do you want to be in a lightning storm? Inside of a Faraday cage. You guys carry that around with you all the time as you hike, right? Your little metallic structure as you go. Social distancing. No, that would be too heavy. Hikers don't like that. So what if you are caught in a lightning storm? Should you get under a tree? Why not? It's a pokey that's full of water. Okay? And water just loves to conduct electricity. Okay? Right? So, yeah, don't stand under a tree. If you can get into a building, yay. If you can get underground, fantastic. Snuggle up to the bear in the cave. There's other dangers there. Under like a highway overpass would be fantastic, a nice concrete type of thing. Okay, but what if you are out somewhere and all you've got is your rain jacket and there's a lightning storm coming? What do? Make sure that your will is all in order. And no, you don't lay down on the ground. Why not? Because you'd be touching the ground, and if the lightning were to strike, say 100 meters or so over there, you would then have the lightning strike pass through your entire body, which again is also a bad day. Okay? So what you do is you try to make yourself the smallest thing, the shortest thing, and the roundest thing, right? Again, we don't want very many pokies if we can avoid it, right? Okay? And notice that I am up on my toes, right? If you can do that squat, you can, if this is more comfortable, but now more of your foot's in contact with the ground, okay? So if possible, you get up on your toes, okay? Scrunch down, make yourself as small as possible, and you ride it out. This way, if the ground is struck near you, it's going to take a path, okay, from your toe, through your leg, through your butt, down to the other toe. You'll probably get knocked on your butt, okay? Or maybe explode in the biggest long jump you've ever done in your entire life, okay? But you will have been saving your vital organs, right, from strikes that go that way. So there you go. There's your practical advice for the day. Go hiking, have fun, don't get struck by lightning. All right. Yeah, should we try? Can we test that? You guys want to go hiking? Just ask. I love hiking. All right. Let's, let me, these pictures are trying to show you kind of what happens in a conductor, right? And they're a little bit weird because you see how they're forcing this conductor. So they've got like charge plates on either side, and then they've got this conductor. Can you see why positive charge on this neutral conductor would get drawn to the negative plate? Yes. Chapter, right, 21. Same thing happens over here on the left-hand side, but opposite signs, right? And the electric field starts on positive, ends on negative. Everything's consistent here. They're trying to point out here that at the surface of a conductor, the electric field always makes a 90-degree angle with the surface. Immediately outside of that surface, it's coming off at 90 degrees. After that, it'll kind of go wherever it wants to go, okay? But we know it comes off at 90 degrees. Even if there's a cavity inside there, what is the electric field going to be inside of these conductors? 0. As long as the charge is not moving through them. That is a bit of a problem. This is not me. I wish it was me, because I would do this in a heartbeat. I think this is amazing. That's a person standing on an insulating stand wearing chainmail with a bunch of Tesla coils around them. That's a little bit closer. I don't know if you can kind of tell, but there's like a metal birdcage type structure around their face. Okay? Why is this person not dead? These are lightning bolts that will kill. These are not Van de Graaff lightning bolts that sort of exist for a very short amount of time and then the more charge needs to build up. Tesla coils can deliver just like continuous lightning bolts of amounts of energy. Okay? So without that shield of that metal suit, this person would be dead. But what is the electric field everywhere inside the metal cage that person is wearing?
0.
It's 0. There's no flow of current. There's no electric field in there. This person is shielded from those bolts. How often does this happen? All the time. All the time. planes are struck by lightning. Why? Where do planes fly? In the sky. Where is lightning found? In the sky. Right? And so airplanes are made out of hopes and dreams. No, metal. Right? What is the electric field inside the airplane? Even when it's struck by lightning? Yes. Is it safe to be struck by lightning when you're inside an airplane? Oh, yes. Happens a lot. Okay. Are airplanes designed with this in mind? Yes. Can airplane systems be shorted out by a lightning strike? Yes. But that doesn't happen very often at all. Because the systems that are carrying electrical signals in an airplane are shielded against such things. And how would you shield a wire against outside electromagnetic interference? Put a metal sheath around it, which is exactly what they do. In fact, the shielding is so good that on an airplane, they have to put the radar on the outside of the metal tube. Does anybody know where an airplane's radar is located? It's right, it's the front nosy bit. On the front of the airplane, okay? That rounded bit at the very front of the airplane is not made of metal, it's made of fiberglass. Why is it made of fiberglass? Because if it were a conductor, what would be the radar signal inside of that dome? 0. Because radar is an electric field. So they have to be clever, right? They have to put a fiberglass dome on the front with the radar dish pointed forward. They want to give it that nice streamlined look for efficiency and no friction and not tearing the radar dome off. But they also want radar signals to be able to go in and out. Radio signals to go in and out of the airplane. So when they tell you that you have to silence your phone and put it into airplane mode when they're flying, why are they asking you to do that?
That's the only signal inside the plane.
Because they don't want to hear you talking on your phone for the whole flight. That is much more of a problem than your cellular phone signals messing up the instruments in the plane. Matter of fact, they can't. There's never been a recorded instance of a cellular device messing up a plane's radar systems, navigational systems, none. They want you to not be on your phone during takeoff and landing especially. Why? Because there's 2 very important times when you are in an airplane. What are they? When you're taking off and when you're landing. Everything else in between is boring and not much happens. Okay? Takeoff and landing is where it's all at. There is one type of interference that can happen and is routinely picked up by airplanes, and it's on the voice radio. They can always tell when somebody is using a telephone close to the cockpit when you can actually hear a type of static in a ATC, the air traffic control communication. You can hear a type of static that is causing interference with the voice communication. And then they'll go into the bathroom where the person's using their phone and tell them to stop. Pilots also know when you have flushed the toilet in the bathroom. How do pilots know that you have flushed the toilet in the bathroom on an airplane? To be clear, there are no cameras and no sensors in the bathroom. It's because the pressure, the internal pressure of the airplane drops momentarily when you flush it. When you flush I'm not sure where this tangent is going, but when you flush a toilet on an airplane, what does it do? It sucks it down, right? There's like a vacuum noise as you flush it, okay? Well, that draws air. And there are instruments in the cockpit that tell the pilots what the cabin pressure is, and momentarily they'll see the pressure dip while the plane tries to repressurize from that suction. Things you didn't want to know about airplane travel. No. No, 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 no. I want to show you something else instead. I have to actually stop the recording